next paper that we're going to cover is a paper by Pacheco-de-Almeida and Zemsky, published in Management Science in 2007, titled The Timing of Resource Development and Sustainable Competitive Advantage. This is a paper that has some important insights on the issue of competitive advantage. It's a theoretical paper in which there is a model where firms initially are heterogeneous, they're different. Some firms have a leadership position because they possess some assets or capability that allow them to get more profits than their rival. And this competitive advantage can disappear over time, so potentially the followers can invest and try to imitate the leaders, developing themselves these resources and capability. And the theoretical setup is very useful to try to understand under what condition you would expect these followers to never try to reach parity and to get rid of the competitive advantage of the leaders, and in what condition instead you would expect these followers to try. And if they try, also the model can tell you in what type of environment you would expect the competitive advantage to disappear very quickly, and what kind of environment in which you would expect the competitive advantage to last for a long period of time, and this investment by followers in terms of imitation to take place only after a particular amount of time. This is an important paper from that perspective, but also I like to cover this paper because it's a very tractable model of timing of investment in a continuous time environment with exponential discounting. This is a tool that can be used for a lot of application in strategy. In a number of environments you may have that firms invest, and you would expect the invest to depend on particular features of the environment. You may have even data on which firm invests to develop a particular asset or to do particular type of activities, and variables that you think are related to it, and you may have information on the timing of this investment. Now, a model like this one is very useful to try to find a theory that links the timing of the investment with other variables that you have and generate predictions, okay, what type of variable you would expect to increase the timing or to reduce the timing, to generate more delay or less delay in the investment and so on. So from that perspective, it's a useful modeling strategy to know. And this paper, in my view, is a very nice, introduction to this type of techniques, and it provides a very tractable setup that can be used in a variety of other applications. We are going to now study the model in the paper of Pacheco-de-Almeida and Zemsky, published in Management Science in 2007. This is a paper in which there are two players, two firms, a leader that we're going to call L, and a follower that we're going to call F. The interaction between these two firms take place in a continuous time setting. So think about time as a continuum. They go from 0 to infinite. And as time passes, the profits that the firm can make in the product market can change. So initially, the two firms are asymmetric. They have different profits. The leading firm has an asset or a resource that is unique and allows it to get a higher profit. We call this profit pi CA, that is the profit of competitive advantage. And the follower has a profit that is pi CD, that is the profit of competitive disadvantage. So at a particular time t, let's call it capital T, things can change in the sense that the follower can develop the resource that before was only owned by the leader. And in that case, the profit becomes the same and become equal to a value here. We're going to call it pi CP, the profit competitive parity. So if there is development at time t, then the profit are going to be the same for the two firms before the leading firm as the profit of competitive advantage and the follower as the profit of competitive disadvantage. And the only assumption that are made on these profits is that the profit of competitive advantage are greater than the profit of competitive parities that are greater from the profit of competitive disadvantage. One notation that you use in the paper is to call delta F the increase in profit between CP, competitive parity, and competitive disadvantage. So the increase in profit made by the follower if the resource is developed and there is no longer competitive advantage but there is competitive parity. Okay, this is called delta F and is assumed to be positive in the sense that your profit go up as a follower if you develop a resource or a capability that before you didn't have and the leading firm had. As I said, there is a continuous time model, and the main question that is analyzed in the paper is whether or not it will be possible, under what kind of environments it will be possible for the follower to really reach competitive parity. So is there any situation in which this capital T cannot exist, is infinite, okay, and always there is a competitive advantage for the leader, is persistent over time? And if instead there are situations in which this capital T can take place, can we have insights on when this should happen? In what kind of environment we should expect competitive advantage not to be persistent and last a long period of time, but to be essentially removed and to have competitive parity very quickly, and in what kind of environment instead we expect this capital T to be very large, so you should expect a persistent competitive advantage for a long period of time. So these are the key questions that are going to be studied in this model. Okay, as I said, this is a continuous time model. As you can see, the profits are obtained every instant in time. And this is actually one of the nice features of this paper is studying this paper will help you learn how to work with exponential discounting in a continuous time model. From the perspective of the leader, if you think about the present value of this profit in case in which there is development at time t of the resource for the from the follower, we can call the present value of this profit as RLT is equal to the integral from 0 to capital T of pi CA multiplied by the exponential of e negative RT dt plus the integral from capital T to infinite of pi CP exponential negative RT dt. So as you can see here is a way in which I compute the net present value with exponential discounting. So for the time period in which I have the CA as profit, that is the period from 0 to t, the profit is going to be CA for each instant, and the net present value, the value at 0 of that instant when exponential discounting, is that profit multiplied by E with the exponent negative RT, where R is the interest rate that is used for the net present value. Then at time t, this changes from time t to the infinite. You have pi CP times E negative RT dt. So this is the net present value of the profits of the leader. And these are the product market profits essentially. And we can do the same thing for the follower. RFT is equal to the integral from 0 to capital T of pi CD E negative RT dt plus integral from T to infinite pi CP E negative RT dt. So again, you have to think about two periods of time. For the period of time until capital T, the follower gets pi CD, that is this one, and this is the way you compute the net present value of a stream in which in every instant you get pi CD from time 0 to capital T, and then from time capital T to infinite you get pi CP, the parity, that is the same as what you have here essentially. Okay, so this is the way we represent the profit, the net present value of the profits for the two firms. The next step to discuss is what is the cost for the follower to develop the resource or the capability at time T. If it is developed at time T, this is the stream of revenues essentially, or product market profits for the follower. But what is the cost? Okay, we're gonna see in the next page how is it the cost is modeled in this paper. Now, in this model, and more generally in timing games like this one, in which the crucial aspect is, how long does it take for something to happen, the costs are assumed typically to be decreasing over time. So if we think about our infinite horizon setup, we have that the cost is typically assumed to behave like this, okay? That initially is very, very expensive to develop something, and as time passes, it becomes cheaper and cheaper and cheaper, okay? And the idea is that at a certain point, it becomes cheap enough that you want to invest and develop the resource. There is a long discussion in the paper about why this structural cost makes sense, and there is also a parameterization of the cost. For this video, we're going to use the simplest form of this parameterization. That is CT is equal to 1 minus S squared capital K squared R divided by E with exponent RT minus 1. So developing the resource for the follower at time T as a cost that is equal to this formula. If you see, as T gets larger, the cost goes down, so it really follows this structure. And as T is equal to, capital T is equal to 0, this becomes 1 minus 1, so you divide it by 0 here in essentially infinite the cost. And as T goes to infinite, essentially this thing becomes smaller and smaller, and then it becomes possible essentially to invest. The parameter here, R is the interest rate, K is essentially the complexity of the resource or the capability. So in a sense, when there is more complexity, the more complex the capability of the resource is, the harder and more expensive it is for a follower to be able to develop it. S is a parameter that captures the spillovers, how much the information, how much the leader is able to keep the information about this capability or resource as confidential. the more information leakage there is, the more the easier essentially it is for the follower to copy. So as you should think about it, going from 0 to 1, as it gets closer to 1, it becomes very easy, it becomes less expensive, less costly for the follower to develop the resource of the capability, because the information required to imitate essentially spills over from the leader to the follower very easily. When as instead is close to 0, this is when the cost is highest. Okay, so these are the parameters. The product 1 minus s times k is essentially the a proxy for the what are called the barriers to imitation that are making it hard to copy the resource and capability. So at the end of the day, the total profit for the follower is equal to the difference between R F T minus C of T. This is the product market profit that I make if I develop the resource capability time T, and this is the cost of developing the resource or capability at time T. And the problem for the follower is really to find a T that maximizes this. What is the optimal T that maximize the difference between essentially the revenue or the returns of developing the capability and its cost? We will have to take the derivative of R and the derivative of T and equate them, and if we find a T that satisfies the equality, we're going to call this T star. It is the optimal time for resource development essentially. If this T doesn't exist, essentially if it only holds at T equal to infinite, it means that there is no way in which the follower can develop the resource and the capability, and in this particular case, the competitive advantage of the leader is going to be long lasting. Is gonna imitation is not going to be possible. So a nice property of this model is that it presents a very tractable setting with exponential discounting. And learning how to play with exponential discounting is very useful, because there are a lot of applications in which you want to study the timing of particular investments in strategy. And also is in general very used in a lot of areas of economics. And the issue is that you can take the function of the returns of the investment of the revenue, this function RFT, it was equal to the integral from 0 to capital T of pi CD E negative RT dt plus the integral from capital T to infinite of pi CP E negative RT dt. And you can take this function that looks very complicated and not very tractable and simplify it dramatically into something much easier to deal with and more tractable for applications. Now I'm going to show you how to get there step by step. But if you are not able to follow this simplification, I really suggest you to look at the basic introductory calculus material, because this is very useful in a lot of application economics. So to be able to deal with this exponential discounting is really important. So the first thing to notice is that here the integrals are respect to t. So the pi's, pi CD and pi CP, are not function of t. So I can take them out of the integral, and I can rewrite this as pi CD times the integral from 0 to t of e negative rt dt plus pi cp times the integral from capital T to infinite of e negative rt dt. Now, the next step is to solve for these two integrals. Remember, to solve for integrals, you need to find a function such that the derivative of that function is equal to this, to e negative rt. And here, the function is equal to negative e with exponent negative rt divided by r. So this is the function that we need for the integral of the exponential discounting. Again, if you're not able to see why this is the function to solve the integral, please revise introductory calculus and the calculus and the related to integration and differentiation of exponential functions. But once I have this function, this can be rewritten as pi cd that multiplies the integral of the exponential from 0 to t plus pi cp times negative e negative rt divided by r that is evaluated at capital T and infinite. The way to go from this to a more tractable formula is really to evaluate this function at capital T and 0 and take the difference between the two. So this is equal to pi cd times negative e negative r capital T divided by r minus this function evaluated at 0. This function evaluated at 0 is the exponential of 0 that is equal to 1. So this becomes plus 1 over r plus pi cp that multiplies this function evaluated at infinite. So e to the minus infinite is equal to 0 plus the function evaluated at capital T, that is e minus r capital T divided by r. So it's the difference between the function evaluated at infinite, the function evaluated at capital T. Evaluated at infinite is 0 minus the function evaluated at t, that becomes plus. Okay. So this, eventually, I can simplify everything to pi cd divided by r times 1 minus e minus r capital T plus pi cp divided by r with e negative rt. And this is the function that is very simple and very tractable with exponential discounting. So if you have like a flow of profits and for a period of time up to t, you have one profit, in this case is pi cd, and then you have from capital T onwards another profit that in this case is pi cp, with exponential discounting to get the net present value is very easy. You just divide this number by r, and then you multiply the profit that you get from the period 0 to capital T by 1 minus e negative rt, and the profit for the period t onwards from equal to pi to e multiplied by e negative rt. So you can see the extremes here. If t is equal to infinite, okay, then these things is equal to 0, and therefore you only get pi cd divided by r, that is pi cd every single instant. If instead t is equal to 0, so immediately you get pi cp, then e minus r0 here becomes 1, and this thing simplifies, and the only thing that you have is pi cp divided by r. Okay, this is a very useful formula, not just for this model, for a lot of application in which you have continuous time and exponential discounting. So I went quite slow in the derivation, but it's something that can be worth understanding in detail because it's useful in a number of potential applications. Okay, now that we have found a simplified version of the revenue function using the exponential discounting, we can go back to the original problem of the follower. It is to maximize the difference between R and C, to find the t that maximizes this difference. It implies to maximize the following function, to maximize with respect to t pi CD divided by R with exponent multiplied by 1 negative e negative RT plus pi CP e negative RT divided by R minus 1 minus s square k square R divided by ERT minus 1. Okay? This is what I need to maximize here to obtain the optimal time. So you need to take the derivative of this thing and set it equal to 0, the derivative with respect to capital T. What is the derivative? Okay, the derivative of this is equal to pi CD divided by R multiplies E negative RT multiplies R minus pi CP divided by R E negative RT multiplies R plus 1 minus S square k square R ERT divided by ERT minus 1 square, and this has to be equal to 0 in the first order condition. Okay, so this is what we need to have satisfied at the optimal t. Again, this requires the derivative of the exponential and requires knowing the derivative of a fraction. So make sure you can follow this, but the derivative of the exponential is just the function itself multiplied by the derivative of the exponent, and the derivative of the fraction, you have the denominator square and then the derivative of the first term times the second minus the derivative of the second term times the first. Okay, this is the idea to get to this formula. I can rewrite this moving this part on the other side of the equality. So I have 1 minus s square k square r, sorry, here there is an r square ERT divided by ERT minus 1 square. This has to be equal to pi CP minus pi CD that multiplies E negative RT. Okay, so the R here simplifies when I move them on the other side, and it becomes this difference here. This difference is what we called at the beginning of the video delta F. So the gain from the follower in going from competitive disadvantage to parity. Okay, so this then can be again simplified by moving this exponential here, and by taking the square root on both sides. We have that 1 minus s k r ERT divided by ERT minus 1 is equal to the square root of delta f. And taking this part here, and dividing everything here, both sides by ERT, we can obtain the following condition, that is the square root of delta f divided by 1 minus s kr is equal to 1 over 1 minus E negative RT. So the optimal t is the t for which this condition is satisfied. And one thing that is important to notice here is that this function here, that is function of capital T, is never less than 1. Okay? This is always greater or equal than 1. If t is equal to 0, this is equal to 1. If capital T is equal to 0, this is equal to 1, and this essentially explodes, is equal to infinite. But as t gets larger, okay, these things tends to 0, and therefore this things here tends to 1. But is always, as long as t is not infinite, this thing here is going to be a bit bigger than 0, and therefore this fraction is going to be greater or equal than 1. This implies that if the square root of delta f, okay, let me move this out. If the square root of delta f divided by 1 minus s capital K R is less than 1, then the condition cannot be satisfied. The condition cannot be satisfied, and an optimal t does not exist. Okay? We cannot find a capital T star. And essentially this can be written as square root of delta f is equal to, is strictly less than 1 minus s times capital K R. If this condition is satisfied, then the resource is not imitable. Okay, there is no way in which the follower will actually imitate the resource and the capability. This is the first important result of the paper, is in proposition 4.1. Okay, so it says that under particular parameters, is the follower will not imitate the leader, even if technically it's possible to invest and develop the resource and the capability. This does not take place. Does not take place if this condition is satisfied. The condition says essentially that this is an environment in which 1 minus s times k is large, so the barriers to imitation are really high, and also is an environment in which delta f is low. This is that the extra profit that I make going from competitive disadvantage to competitive parity is low. So in a sense, the model tells you that competitive advantage will not go away when barriers of imitation are high. But more interestingly, high here is a relative high. It means that it depends how costly it is to imitate relative to the gains of imitation. If the gains of imitation are low, even if it's not extremely costly to imitate, imitation will not take place. Okay, we have seen conditions under which there is no development of the resource or the capability by the follower. But if these conditions are not satisfied, it means that we can find a capital T in which 1 over 1 minus E negative RT is equal to the square root of delta F divided by 1 minus S capital KR. Means that this is a capital T at which the resource capability is developed. Okay, the resource capability is developed. And this can be a very useful formula to derive. This is that you may have a lot of settings in which you have data of the time required by companies in performing a particular investment, and you want to see how some other variables that you have may affect that timing. By using formula like this, you can then obtain a formula for the time and see how the time changes depending on the other variables, and then test this empirically. So here, for example, we can obtain a function of the optimal time t as function of delta F, S, and K. And if you have data on things like the complexity, on data on spillovers, then you can see whether in the data the relationship with the development time is consistent with what the theory would predict. So let's find this optimal time. We have essentially to solve this equality for capital T. To do this, we rewrite this as 1 minus e with exponent negative RT is equal to 1 minus S, then multiply capital KR divided by square root of delta F. This can be rewritten as E with exponent RT is equal to 1 minus S capital KR divided by square root of delta F with everything with exponent negative 1. So here essentially I move this on the other side, and these two, I switch side of these two, and also I took the inverse of both sides in order to get rid of the negative r in the exponent. And now to get rid of the exponential, essentially I take the logarithm on both sides. So this is equal to RT is equal to the logarithm of 1 minus S capital KR divided by square root of delta F with exponent negative 1. And getting, the R on the other side, I obtain the optimal T star, that is 1 over R is equal to the log, T star is equal to 1 over R that multiplies the log of 1 minus S capital KR divided by square root of delta F exponent negative 1. And essentially this is the key formula for proposition 4.2 in the paper, and it gives you a function of the optimal time of development of the resource as function of the variables in the model that are S, K, R, and delta F. And by taking the derivative of this with respect to the variables, you obtain the relationship that the model predicts between the development time and these variables. So for example, here you can see the delta T star respect to S is negative. The derivative of T star respect to K is positive, and the derivative of T star respect to delta F is negative. Okay, sorry, let me move it higher so that you can see. And in this particular model, this tells you that you should expect a very quick development in terms of timing of the resources when the spillovers effect are large and when the gain from reaching competitive parities are high. And you should expect a longer time for the development of the resource when the complexity is high. But in general, as I said before, this is a really useful tool, because if you have data that are data of timing, in which firms need to develop a particular resource or take some action or make some investment, and you have some idea that the cost of doing that investment depends on some particular variables, then a model like this gives you a link between the time in which the investment takes place and these variables, and some predictions that then you can take to the data and test empirically.